Hello everyone, it's BioDare and I dare you to use it. In this video I'm going to talk about trends, but not the fashion trends, but trends in your data and how they affect period analysis. We prepared synthetic data of known 24 hours period, to which different forms of baseline trends have been added. We have linear trend, then exponential trend that rises faster at the end, very similar trend form that also rises faster at the end, but is based on different function than exponential. Then more complicated trend, which I call two-third hill, which reaches plateau at the end. And finally one called hill that goes up in the middle and then falls down again. These types of trends are based on waveforms we have seen in the real biological data, so they cover typical cases you may encounter in your research. Let's analyze the data and see how they affect the period values. I'm going to analyze the data with FFT and LS. Our synthetic data have known period of 24 hours. For linear trend, we got the correct results. For exponential trend, we see that estimated periods are in average half an hour shorter. The simple trend that rises faster at the end does not affect the results. But there is obviously a problem with the last two complex trends. The trend with the plateau at the end has only one result, and the hill shape got no results at all. Let's try to do the analysis with the linear detrending. Linear detrending is the default option for the analysis. Let's check its effect on the data. Obviously, the linear trend was removed. Exponential trend was transformed into this symmetrical arc. And similarly, other trends were transformed into arcs or remained unchanged like the hill shape. Let's analyze the data. Once the results are back, we can observe similar behavior as for the raw data. Good estimates for linear trend and no results for the complex trends. Actually, if we compare these results with the one for the raw data, we can see that they are exactly the same. The reason why is that all the methods perform some form of linear detrending before proper analysis. So what the methods actually analyze looks like our detrended data. And that is why the linear detrending is the default option, so you can see similar data to the one that methods will process. Let's try to understand why we could not get the results for the complex trends. I will click on Select Period to check the data and the analysis fit. In the case of two-third hill, the detrended data looks like this big arc with oscillations on top of it. And FFT and LS, instead of finding those little waves, fitted just one curve that followed the trend instead. Apparently, adding extra components to reproduce the oscillation was not improving fit enough, so the method stopped after finding the baseline trend in the data. If we check the other trend, the hill one, we will see the same problem. Again, method fitted the general baseline trend in the data instead of the circadian oscillations. And this is the main problem with the large trends in the data. Instead of circadian components, methods pick up only the baseline trend. Let's check if the other form of the detrending can solve the problem. I will try cubic detrending. If you look at the data, it clearly removes all the baseline trends. Now the data are flat, with easily distinguished oscillations. So let's analyze them. Once the results are back, we got the average period around 24 hours for all the forms of the trends. We will experience similar problems with other methods of period analysis, especially the ones that are based on curve fitting. For example, M4 fit. On a linear trend gives correct periods. Periodogram also fails on the last two complex data. But it turns out that MESA, which is not fit-based, is generally more resilient to baseline trends. As you can see, MESA with linear detrending gives really good estimates, close to 24 hours for all the data. However, even MESA fails if the baseline trend is more pronounced. For example, when the trend range is 10 times larger than amplitude of the oscillations. We have seen effect of the baseline trends, but what about the amplitude trends, or amplitude dampening to be more specific? We prepared similar synthetic data of known 24 hours period, but with different levels of signal dampening. As you can see, the signal gets weaker and weaker at the end of the data. In our last test data, the signal at the end is only 10% of its initial value. So what happens if we analyze this kind of time series? I use FFT and LS, And as you can see, we got a really good period estimates of 24 hours of average period, even for the data that lost 90% of its initial signal. But our time series are 5 days long, so even the highly dampened ones still have few initial days of strong signal. We prepared another dataset that contains only 3 days of data, so the highly dampened data lose already half of its initial signal on the second day. The FFT-NLS still finds periods around 24 hours, but we can observe a bit wider distribution of the results. Even the highly dampened data still produces good average value. Let's try our other methods of choice, MESA. It turns out that MESA is more sensitive to dampening than FFT-NLS. For the highly dampened data, the estimated periods are significantly deviated from the 24 hours period. Nevertheless, even if we lose more than half of the signal, we still are getting estimates close to 24 hours. Let's check if we can improve the results with amplitude detrending. I select baseline and amplitude detrending for the input data. If we check the time series, we can see that indeed this kind of detrending removed the dampening, and all of the oscillations have similar strength even for the weak original signal. After analysis with MESA, we are getting average period of 24 hours for all of the time series. So the detrending worked. To summarize, typically there is no need for amplitude detrending. The methods are resilient to it, and moreover this kind of detrending can introduce artifacts at the edges of the data. However, you should check for the baseline trends. The time series should be relatively flat, with clearly visible oscillations. And you should avoid having curved trends in the data, especially when using FFT-NLS. Thank you, and see you next time!